So first came Softmax Attention, and Softmax Attention works beautifully until you scale it. The problem is computation. If we have T tokens and feature dimension D, self-attention computes a T by T attention matrix. That means the complexity is proportional to T squared. Now in language models, T is the sequence length. But in vision transformers, T itself scales with image resolution squared. So if you double the resolution of an image, the number of tokens increases by 4. And since attention is quadratic in tokens, the total computation increases by 16 times. That's fourth power scaling with resolution. And so we need something better. Then came linear attention. The idea is simple. Instead of computing QK transpose directly, we use a kernel trick. We rewrite attention as phi of Q times phi of K transpose. This term. Then we reorder the multiplications. Instead of computing T by T first, we compute phi of K transpose times V. Now the complexity becomes linear in T. That solves the context length problem. But there's still an issue. The computation is now proportional to T times D squared. So while it's linear in tokens, it's still quadratic in feature dimension. If D is large, this is still expensive. So linear attention solves half the problem. Now here's the interesting observation. In multi-head attention, we divide features across H heads. In softmax attention, increasing H doesn't change total compute. But in linear attention, something strange happens. The complexity becomes proportional to T times D squared divided by H. So as we increase the number of heads, the computation actually decreases. That's the key insight. So the researchers asked, what if we push this to the extreme? What if we set the number of heads equal to the feature dimension, or H equals D? Now each head gets only one feature. Each head processes a scalar, and suddenly the complexity becomes T times D, linear in tokens and linear in features. That is Hydra Attention. But Hydra does something more interesting. Instead of full token to token mixing, it first aggregates a global feature. Sum over all tokens of phi of k, actually this must be phi of k, multiplied element wise with v. This creates one global vector. Then each token uses phi of q to gate that global feature. So Hydra mixes information through a global bottleneck, not through pairwise interactions like softmax. And surprisingly, with the right kernel, especially cosine similarity, this works extremely well. In fact, replacing later attention layers with Hydra can even improve accuracy.